Welcome back to Science Sleep Stories. Tonight we're embarking on a journey through the most perplexing, beautiful and utterly baffling mysteries that science has yet to solve. Before we begin, if you enjoy these relaxing deep dives into the wonders of science, please take a moment to like this video and subscribe to the channel. It really helps us continue creating these stories for you. And if you're comfortable, let us know in the comments where you're watching from and what time it is in your part of the world. It's always fascinating to see our global community coming together to explore the unknown. Now get comfortable, adjust your pillows, dim the lights, maybe put on some comfortable headphones. Tonight we're going to explore the edges of human knowledge, those tantalizing questions that keep scientists awake at night and fill us with wonder during the day. We'll travel from the depths of space to the inner workings of your own mind, from signals that might be alien messages to forces we cannot see but know must exist. These aren't ghost stories or fantasy. These are real mysteries, supported by evidence, studied by the brightest minds humanity has produced, and yet they remain stubbornly, beautifully unexplained. So let's begin our journey into the unknown. Science has given us so much. We've mapped the human genome, split the atom, sent spacecraft beyond our solar system, and captured images of black holes billions of light years away. We understand the chemical reactions that power stars, the forces that hold molecules together, and the evolutionary processes that shaped every living thing on Earth. We can predict eclipses centuries in advance, cure diseases that once devastated entire civilizations, and communicate instantly with someone on the other side of the planet. And yet, for all our knowledge, for all our technological prowess and mathematical sophistication, there remain questions we simply cannot answer. Not because we lack the instruments or the intelligence, but because these mysteries cut to the very heart of what reality is, how it works, and what our place might be within it. These aren't the mysteries of mythology or superstition. These are rigorous, evidence-based conundrums that emerge directly from our best scientific observations. They're the questions that arise when we look at the data and realize something fundamental doesn't add up. When the math works perfectly, but leads to conclusions that seem impossible. When our instruments detect something that shouldn't exist, or fail to detect something that absolutely must be there. What makes these mysteries so captivating isn't just that they're unsolved, it's that they often reveal how much we don't know about the universe we inhabit. Every answer science provides opens up new questions, deeper layers of mystery. The more we discover, the more we realize how vast the unknown truly is. It's humbling and exhilarating in equal measure. Think about it this way. A few centuries ago, humans looked up at the night sky and saw pinpricks of light. We called them stars, but we had no idea what they were. Were they holes in the celestial sphere? Distant lanterns? Divine beings watching over us? Today we know stars are massive thermonuclear furnaces, fusing hydrogen into helium through processes we can describe with precise mathematical equations. We can measure their temperature, composition, age and distance. We can predict their entire life cycle from birth in stellar nurseries to death as white dwarfs, neutron stars, or black holes. That's an extraordinary achievement. We went from complete ignorance to comprehensive understanding in just a few hundred years. But that understanding didn't eliminate mystery. It revealed deeper ones. Now we know that the matter making up those stars and us, and everything we can see, constitutes only about 5% of the total contents of the universe. The other 95% is something else entirely, something we've never seen, never touched, never directly detected. We've given it names, dark matter and dark energy, but those names are placeholders for our ignorance. We know these things exist because of their effects, but we have no idea what they actually are. That's the kind of mystery we're exploring tonight. Not the mysteries of things we haven't discovered yet, but the mysteries embedded in the very fabric of what we have discovered. The anomalies, the paradoxes, the observations that refuse to fit neatly into our understanding of how reality works. Science thrives on these mysteries. They're not embarrassments or failures. They're invitations to think deeper, look harder, and question our most basic assumptions. Every major breakthrough in scientific history came from grappling with a mystery that seemed unsolvable. Quantum mechanics emerged from mysteries about the behavior of light and atoms. Einstein's relativity arose from mysteries about the speed of light and the nature of gravity. Evolution explained the mystery of Earth's stunning biological diversity. The mysteries we're exploring tonight are the frontiers of current science. They're the questions keeping physicists, astronomers, biologists and neuroscientists up at night, scribbling equations, running simulations, building new instruments, and proposing bold theories. Some of these mysteries might be solved in your lifetime, others might puzzle humanity for centuries or millennia, and a few might be questions we're simply not equipped to answer, limitations built into the very nature of consciousness and cognition. But there's beauty in that uncertainty. There's wonder in knowing that despite all our progress, we still live in a universe full of secrets, that we can stand at the edge of the unknown and peer into its depths, even if we can't yet illuminate what lies there. So tonight, as you drift towards sleep, let these mysteries wash over you. Don't worry about solving them. Don't stress about understanding every detail. Just let yourself feel the sense of awe that comes from contemplating how strange, how vast and how magnificent our universe truly is. Let's explore these enigmas not with anxiety, but with the calm curiosity of someone gazing at stars on a clear night, comfortable with not having all the answers, content to simply wonder. Our first mystery takes us back to a summer night in 1977, to a radio telescope in Ohio, and to 72 seconds that have sparked debate, speculation, and wonder ever since. It was August 15th, 1977. Elvis Presley had just died. Star Wars was dominating movie theatres. The world was a different place, but in a small observatory in Delaware, Ohio, something extraordinary was about to happen. Something that would capture imaginations for decades and become perhaps the most famous potential signal from extraterrestrial intelligence ever detected. The location was Ohio State University's Big Ear Radio Telescope, an enormous structure that looked less like a telescope and more like a football field with metal walls. This wasn't designed to observe visible light. Instead, it listened to radio waves from space, the faint electromagnetic whispers that traverse the cosmos. The Big Ear had been repurposed a few years earlier for a specific mission as part of the search for extraterrestrial intelligence, or SETI. Its task was simple, but profound. Listen for signals that might indicate intelligent life beyond Earth. The telescope operated automatically, scanning the sky as Earth rotated, recording any interesting radio signals it detected. The data was printed out on continuous sheets of paper, marked with alphanumeric characters representing the intensity of detected signals. Each night produced reams of printouts, most showing nothing but background noise, the random static of the universe. A few days after August 15th, a volunteer astronomer named Jerry Amon was reviewing these printouts at home. He was doing what he'd done countless times before, scanning columns of numbers for anything unusual. Most nights, there was nothing. Just the expected background radiation, occasional interference from Earth-based sources, maybe a distant quasar or pulsar showing up in predictable ways. But then he saw it, a sequence that made his heart skip. 6EQUJ5. In the Big Ear's coding system, these characters represented signal intensity. The telescope used a simple scheme where higher numbers and letters represented stronger signals. Most background noise registered as ones or twos. Occasionally, random fluctuations might produce a 3 or 4, but this sequence went from background level to the strongest possible reading the system could record, held there for several measurements, then dropped back down. The pattern was perfect. It matched exactly what you'd expect to. See if a powerful narrowband radio source had drifted through the telescope's field of view as Earth rotated. Eamon was so astonished that he grabbed a red pen and circled the sequence. In the margin, he scrawled a single word: "Wow!" That exclamation gave the signal its name, but it also captured the sheer surprise and excitement of the moment. This wasn't just any signal. This was potentially something extraordinary, and here's why. The signal had been detected at a frequency of 1420 MHz, right in the middle of what radio astronomers call the waterhole. This is a quiet region of the electromagnetic spectrum centered around the natural emission frequency of neutral hydrogen, the most abundant element in the universe. The waterhole is protected from human radio transmissions by international agreement. It's a natural choice for anyone wanting to send a signal across interstellar space. Any technological civilization would know about hydrogen. They'd know this frequency. If you wanted to say, "Hello, we're here," to the cosmos, this is where you'd broadcast. The signal's characteristics were even more intriguing. It was narrowband, meaning it was concentrated at a very specific frequency rather than spread out across a range. Natural cosmic phenomena, like pulsars or quasars, tend to produce broadband emissions scattered across many frequencies. Narrowband signals are associated with artificial transmissions like radio or television broadcasts. They suggest a deliberate, focused emission rather than random noise. The intensity was remarkable too. The signal was 30 times stronger than the background noise, strong enough to stand out dramatically but not so strong as to be nearby interference. It lasted exactly 72 seconds, which was precisely how long the Big Ear could observe any single point in the sky as Earth's rotation carried it through the telescope's field of view. This temporal pattern matched what you'd expect from a distant stationary source, not from something moving near Earth like a satellite or aircraft. And perhaps most tantalizingly, the signal appeared to come from a specific direction in the sky, from the constellation Sagittarius, in a region where no known natural radio sources could account for such an emission. No pulsar, no quasar, no distant galaxy. Just empty space, or so it seemed. Eamon and his colleagues at Ohio State University were both excited and cautious. The first rule of SETI is that extraordinary claims require extraordinary evidence. One observation, no matter how compelling, isn't enough to declare contact with alien intelligence. You need confirmation. You need to detect the signal again, study it more closely, rule out every possible mundane explanation. So they tried. They turned the Big Ear back to that same patch of sky and listened again, and heard nothing. They listened for days, weeks, months. Still nothing. Other radio telescopes around the world were alerted and they pointed their dishes towards Sagittarius. The Very Large Array, far more sensitive than the Big Ear, scanned that region repeatedly. Still nothing. The signal, whatever it was, had appeared once and then vanished, like a whisper in the dark that you're not entirely sure you heard. This lack of repetition has been both frustrating and fascinating. In science, reproducibility is crucial. If you can't detect something again, it's very hard to study it or confirm what it was. But the lack of repetition doesn't necessarily mean the signal wasn't real or important. Think about it from the perspective of an alien civilization trying to make contact. Would they broadcast continuously in all directions forever? That would require enormous amounts of energy. More likely, they might send targeted beams, sweeping across the sky like a lighthouse, each beam illuminating a particular direction only briefly before moving on. Earth might have just happened to be in the path of such a beam for those 72 seconds in August 1977, and we've never aligned with it again since. Or maybe the signal wasn't meant as communication at all. Perhaps it was leakage from some alien technology, the extraterrestrial equivalent of radio waves escaping from Earth into space, or the aftermath of some cosmic event we don't understand, or something even stranger. Over the decades since its detection, scientists have proposed numerous explanations for the WOW signal, and this is where our story gets really interesting because it showcases how science grapples with mysteries, testing hypotheses, gathering new data, refining understanding. Initially, the most mundane explanations were considered. Could it have been terrestrial interference? A passing airplane or satellite that happened to emit radio waves at just the right frequency? Detailed analysis made this unlikely. The frequency was in a protected band where no Earth-based transmissions were supposed to occur. No aircraft or satellites were known to be in that part of the sky at that time, and the signal's characteristics didn't match typical interference patterns. Could it have been a natural astrophysical phenomenon? Some new type of cosmic event we'd never seen before? This remained possible but puzzling. No known natural processes produce such a narrow band, brief, intense signal at that specific frequency. Pulsars produce regular pulses, but at different frequencies and with different characteristics. Quasars emit radio waves, but continuously, not in a brief burst. Whatever natural explanation might account for the wow, signal would have to be something previously unknown to science, which is itself intriguing. Then, in 2017, nearly 40 years after the original detection, an astronomer named Antonio Paris proposed a novel hypothesis. He suggested the signal might have come from comets, specifically two comets, named 266P Christensen and 335Ps Gibbs, that were in the same region of sky during 1977, though they hadn't been discovered yet. At that time, Paris theorized that these comets could have been surrounded by clouds of hydrogen gas, which naturally emit radio waves at 1420 MHz. If the Big Ear had observed one of these hydrogen clouds, it might have detected a strong 1420 MHz signal. This explanation was appealing because it was testable. The comets still exist and still orbit the Sun, so Paris could observe them with modern radio telescopes to see if they produced wow-like signals. He did observe them and did detect some radio emissions at the right frequency. Case closed. Not quite. Other astronomers quickly pointed out problems with the comet hypothesis. The radio emissions Paris detected from the comets were much, much weaker than the original wow signal. Even accounting for different distances and observing conditions, the intensity didn't match. Moreover, if comets routinely produced such strong radio signals, we should have detected many wow-like events over the years. Comets are common. But the wow signal remains unique. The scientific community largely rejected the comet explanation, but it highlighted an important principle. Good science means proposing testable hypotheses and being willing to abandon them when evidence doesn't support them. The fact that Paris could test his idea and others could critique it is exactly how science should work. More recently, in 2024, a new analysis emerged that might bring us closer to understanding the wow signal, though it moves away from the exciting possibility of alien communication. A team led by astrobiologist Abel Mendez at the University of Puerto Rico at Arecibo reanalyzed decades of old data from the Ohio State SETI program using modern computational techniques. They also examined data from the former Arecibo Observatory, searching for similar signals. They found something intriguing. In Arecibo's data from 2020, they detected several weaker signals that resembled the wow signal, appearing at the same frequency and with similar characteristics, just not as intense. These mini-wow signals gave them new clues. Based on this additional data, Mendez and his colleagues proposed that the wow signal and similar events might be caused by a rare astrophysical phenomenon involving interstellar clouds of neutral hydrogen being bombarded by intense radiation. Specifically, they suggest a scenario where a powerful flare from an object like a magnetar, an extremely magnetic neutron star, strikes a cloud of hydrogen in interstellar space. This collision could briefly create conditions where the hydrogen cloud acts as a maser, the radio equivalent of a laser, amplifying radio waves at the 1420 MHz frequency to enormous intensity. This would explain why the signal was so brief and intense, and why it hasn't been seen again. Magnetoflares are rare and random. The alignment needed, where a flare hits a hydrogen cloud that's positioned just right for us to detect the resulting radio burst, would be extraordinarily unlikely. We might go decades or centuries between such events visible from Earth. It's an elegant hypothesis that doesn't require aliens or unknown physics, just rare cosmic alignments of known phenomena. But here's the thing, it's still speculation. The team's paper is going through peer review, and not all scientists are convinced. The details of how a magnetoflare would create such a signal aren't fully worked out. Some researchers think there are gaps in the explanation, details that don't quite fit, and that's okay. That's how science progresses, through proposals, testing, debate, and gradual refinement of understanding. The wow signal might eventually be fully explained as a natural phenomenon, or we might discover it was something else entirely, or it might remain forever ambiguous, a tantalizing glimpse of something we can't quite pin down. But here's what makes the wow signal so captivating beyond the possibility of alien contact. It represents a moment of genuine mystery in the scientific process, a moment where our instruments detected something unexpected, something that doesn't fit neatly into our categories. Whether it was aliens, a magnetomaser, or something we haven't even thought of yet, those 72 seconds in August 1977 reminded us that the universe is still full of surprises. The wow signal also highlights the patience required in the search for extraterrestrial intelligence. SETI scientists have been listening to the cosmos for over 60 years. They've examined millions of stars, scanned billions of radio channels, sifted through unimaginable amounts of data. The wow signal is the closest they've come to finding something that might, possibly, maybe, be a transmission from another civilization. One signal in 60 years. One moment of wow amid decades of silence. That silence is itself a mystery we'll explore more deeply later, but for now consider what it means. The fact that we've heard so little might tell us something profound about the universe. Maybe intelligent life is incredibly rare. Maybe it exists but never develops radio technology. Maybe civilizations rise and fall too quickly for their signals to overlap in time and space. Or maybe, just maybe, everyone else is listening too, waiting for someone else to make the first move, afraid of what might happen if they reveal themselves. Jerry Amon, the astronomer who discovered the wow signal, has been cautious about its interpretation throughout his life. When asked directly if he thinks it was an alien transmission, he's careful not to commit. He says it certainly has the characteristics of what a signal from extraterrestrial intelligence might look like. But he also acknowledges that without confirmation, without detecting it again, we can't be certain. The honest scientific answer is we don't know, and sometimes that's the most profound answer of all. As you settle deeper into relaxation tonight, think about those 72 seconds. Imagine the moment Amon saw that sequence of characters on the printout. That instant of recognition, of wondering, could this be it? Are we finally seeing proof we're not alone? The excitement, the doubt, the careful analysis that followed. And think about the signal itself, travelling through space for who knows how long, perhaps from a source hundreds or thousands of light years away, finally intersecting with our little radio telescope on a summer night in Ohio. Whether it was aliens or hydrogen clouds or something else entirely, the wow. Signal reminds us that mystery still exists in our universe, that for all our telescopes and computers and mathematical sophistication, we can still be surprised. We can still see something that makes us say wow and wonder what it means. Now let's turn our attention to a mystery that's even larger, even stranger. A mystery that involves not just a signal, but the entire structure of the cosmos itself. Look up at the night sky on a clear evening away from city lights. You'll see thousands of stars, the Milky Way streaming across the heavens. Perhaps a planet or two. It's beautiful, awe-inspiring, a window into the immensity of space. But here's something that will change how you think about that view forever. Everything you're seeing, every star, every galaxy, every nebula, every particle of glowing gas, all of it combined represents less than 5% of the total contents of the universe. Let that sink in for a moment. All the matter we can see, the stuff that makes up stars and planets, that forms our bodies and everything around us, is a tiny fraction of what actually exists. The other 95% is invisible. We can't see it with our eyes or with telescopes, no matter how powerful. It doesn't emit light, doesn't absorb light, doesn't reflect light. For all practical purposes, it's ghost matter, phantom substance that we know exists only because of its gravitational effects on the visible universe. Scientists call this invisible material dark matter, and understanding what it is has become one of the most pressing challenges in all of physics. The story of dark matter begins not with astronomers looking through telescopes, but with astronomers doing math. In the 1930s, a Swiss astronomer named Fritz Zwicky was studying a collection of galaxies called the Coma Cluster. He wanted to understand how these galaxies moved relative to each other, so he measured their velocities and calculated how much mass the cluster must contain to keep all those galaxies gravitationally bound together. When he did the math, something was very wrong. The galaxies in the Coma Cluster were moving far too fast. Given the amount of visible matter he could see, all those stars and gas clouds, the galaxies should have been moving much more slowly. If they were really going as fast as his observations indicated, they should have escaped the cluster's gravity long ago and scattered into intergalactic space. But they hadn't. The cluster was stable. Something was holding it together. Zwicky calculated that the cluster must contain about 400 times more mass than he could see. There had to be huge amounts of invisible matter, dark matter as he called it in German, providing the additional gravity needed to keep the galaxies from flying apart. At the time, most astronomers dismissed Zwicky's findings. Maybe his observations were wrong, maybe his calculations were off, maybe he'd overlooked some visible matter. The idea that 99% of the universe might be invisible seemed too radical, too bizarre to take seriously. Then, in the 1970s, an American astronomer named Vera Rubin conducted a series of observations that would change everything. Rubin was studying spiral galaxies, measuring how fast stars at different distances from the galactic centre were orbiting. This was relatively straightforward observational astronomy, the kind where you expect boring, predictable results confirming what you already think you know. But what Rubin found wasn't boring at all. It was revolutionary. According to the laws of gravity as Isaac Newton described them, and as Einstein refined them, stars farther from the centre of a galaxy should orbit more slowly than stars near the centre. This is how our solar system works. Mercury, close to the Sun, orbits rapidly. Neptune, far from the Sun, crawls along at a comparative snail's pace. The farther you get from the gravitating mass, the weaker the gravity, the slower the orbit. But when Rubin measured the speeds of stars at the edges of spiral galaxies, she found they were moving just as fast as stars near the centre. In some cases, they were moving even faster. The orbital speed stayed constant or even increased with distance, a pattern called a flat rotation curve. This made no sense according to conventional gravity unless there was far more mass in those galaxies than the visible stars could account for. Just like Zwicky decades earlier, Rubin was seeing evidence for invisible mass. But her observations were more detailed, more extensive and harder to dismiss. She studied galaxy after galaxy and found the same pattern everywhere. Flat rotation curves, stars moving too fast, missing mass. The scientific community had to take it seriously now. Two independent lines of evidence separated by decades pointed to the same conclusion. Galaxies, and indeed the entire universe, contained vast amounts of matter we couldn't see. But what is this dark matter? That's the mystery that has consumed physicists for the last 50 years. We can actually rule out a lot of possibilities pretty easily. It's not ordinary matter that just happens to be dark. It can't be black holes, at least not in sufficient numbers. We detect black holes through their gravitational lensing effects and other signatures, and we don't see enough. It's not rogue planets, or brown dwarfs, or any other form of normal matter that doesn't shine. Extensive searches have shown these objects exist, but nowhere near abundantly enough to account for all the missing mass. So if it's not regular matter, what is it? The leading hypothesis is that dark matter consists of particles that simply don't interact with electromagnetic radiation. Remember, the only reason we can see ordinary matter is that it interacts with light. Atoms absorb photons, emit photons, reflect photons. That's how vision works, how telescopes work, how all our traditional observational tools work. But what if there are particles that don't do any of that? Particles that don't interact with photons at all, that pass through electromagnetic radiation like ghosts walking through walls. Such particles would be invisible by definition. You could never see them, never photograph them, never detect them with any light-based instrument. But they would still have mass, and mass means gravity. They'd pull on ordinary matter, affecting how galaxies rotate, how galaxy clusters hold together, how the large-scale structure of the universe formed. This is what physicists think dark matter is. A new type of fundamental particle, or perhaps several types, that interact with regular matter only through gravity. They've given potential candidates names like WIMPs, which stands for weakly interacting massive particles, and axions, which would be extraordinarily light particles that fill space like a kind of particle fog. The evidence for dark matter has only strengthened over the decades. Beyond galaxy rotation curves, astronomers have found dark matter's fingerprints everywhere they look. When they study gravitational lensing, the bending of light around massive objects that Einstein predicted, they find that clusters of galaxies bend light far more than their visible mass should allow. There's extra mass there, invisible mass, warping space-time. When they examine the cosmic microwave background, the afterglow of the Big Bang, they find patterns in its temperature fluctuations that only make sense if dark matter exists and has been shaping the universe's structure since the beginning. When they simulate the formation and evolution of galaxies on supercomputers, they find that the simulations only match what we actually observe in the real universe if they include dark matter. Without it, galaxies don't form properly. The large-scale structure of the cosmos, the way galaxies cluster together in vast filaments and sheets with enormous voids between them, only makes sense if dark matter exists. One of the most dramatic pieces of evidence comes from studying collisions between galaxy clusters. When two massive clusters of galaxies collide, the visible matter, mostly hot gas between the galaxies, slams into itself and slows down. It's like two cars crashing. But dark matter, if it only interacts through gravity, would pass right through itself like two clouds of fog intersecting. The dark matter from each cluster would continue onward, largely unaffected. Astronomers have observed exactly this scenario in a system called the Bullet Cluster. They can see the hot gas glowing in X-rays piled up in the middle where the collision happened. But when they measure gravitational lensing to find where most of the mass actually is, they find it's not where the visible matter is. The mass is located where the dark matter from each cluster passed through and kept going. The dark matter and visible matter have separated just as theory predicts. It's as close as we've come to directly observing dark matter's effects, so the evidence is overwhelming. Dark matter exists. We know how much of it there is, roughly 27% of the universe's total mass energy content. We know where it is, surrounding and interpenetrating every galaxy, including our own. We know what it does, providing the gravitational scaffolding that allowed galaxies and large-scale structure to form. We even have a rough idea of how it's distributed in space. But we don't know what it is. Dozens of experiments around the world are trying to detect dark matter particles directly. These experiments are often located deep underground to shield them from cosmic rays and other background radiation that might create false signals. They use incredibly sensitive detectors, often cooled to nearly absolute zero, waiting for the moment when a dark matter particle might interact with normal matter. The idea is simple in concept. Even though dark matter rarely interacts with ordinary matter, if you have enough detector material and wait long enough, eventually you should see an interaction. A dark matter particle passing through your detector should, very occasionally, bounce off a nucleus in the detector material, creating a tiny burst of energy that can be measured. So far, after decades of searching with increasingly sensitive instruments, we haven't definitively detected a single dark matter particle. We've set limits on what dark matter can't be, ruling out certain theoretical possibilities, but we haven't found it. This is frustrating, but also exciting in its own way. It means dark matter is even stranger than we initially imagined. Whatever it is, it's remarkably elusive, interacting with ordinary matter even less frequently than we expected. The mystery deepens rather than resolves. Some physicists have proposed that maybe dark matter isn't particles at all. Maybe it's something even more exotic, modifications to gravity itself that we don't yet understand. Perhaps Einstein's general relativity, incredibly successful as it has been, breaks down on galactic scales in ways we haven't recognized. Maybe the force of gravity behaves differently over vast distances than our equations predict. These modified gravity theories can explain some observations, but they struggle with others. Most physicists still favour the particle hypothesis because it's simpler and explains more of the data. But the modified gravity ideas haven't been ruled out entirely. Science stays open to possibilities even when they challenge deeply held assumptions. Living in a universe where 95% of the content is invisible challenges our intuitions about reality in profound ways. We think of the universe as being made of stuff we can see and touch. Atoms, molecules, stars, planets. But most of the universe is something else, something we've never directly encountered. Something that might be made of particles that have never interacted with anything on Earth except through their gravity. Right now, as you lie there, dark matter is passing through you. Millions of dark matter particles are streaming through your body every second, through the Earth, through the walls, through everything. They don't interact with your atoms, so you can't feel them. They just pass through like you're not even there. Your entire life you've been immersed in a sea of dark matter without ever knowing it. There's something humbling about that, about recognizing how much of reality escapes our senses and instruments. But there's also something wonderful about it, a reminder that the universe is stranger and richer than we imagine, that mysteries persist even in our age of scientific sophistication. The dark matter mystery will likely be solved eventually. Some clever experiment will detect a particle, or some theoretical breakthrough will explain the observations in a new way. When that happens, it will be one of the great triumphs of human science, revealing a hidden aspect of reality that's been there all along, just outside our ability to perceive it directly. But for now, dark matter remains one of the most beautiful and tantalizing mysteries in science, known to exist, crucial to the universe's structure, and yet utterly invisible and undetected. A ghost universe surrounding and interpenetrating our own, influencing everything, and yet remaining hidden from view. As you drift towards sleep tonight, imagine that invisible universe, all that dark matter, more massive than all the visible stars combined, shaping the cosmos in ways we're only beginning to understand. Feel its presence even if you can't detect it, knowing that there's so much more to reality than what we can see. If dark matter is mysterious, then dark energy is doubly so. Not only do we not know what it is, but its very existence suggests that most of what we thought we understood about the universe might be wrong. Dark energy might be the strangest thing science has ever discovered, and it might determine the ultimate fate of everything that exists. The story of dark energy begins with one of astronomy's greatest discoveries. In the 1920s, an astronomer named Edwin Hubble, using what was then the world's most powerful telescope, was studying distant galaxies, trying to measure their distances and velocities. What he found was shocking. Nearly every galaxy he observed was moving away from us. The universe wasn't static, it was expanding. This discovery revolutionized cosmology. If galaxies are moving apart now, they must have been closer together in the past. Trace that expansion backward in time, and you reach a point where everything in the universe was compressed into an infinitely dense point. This was the origin of Big Bang theory, The idea that the universe began in an incredibly hot, dense state and has been expanding and cooling ever since. For decades after Hubble's discovery, astronomers asked a natural question about this expansion. Was it slowing down? After all, gravity pulls everything together. The gravitational attraction between all the matter in the universe should be acting as a brake, slowing the expansion over time. Maybe the expansion would eventually stop and reverse, leading to a big crunch where everything collapses back into a singularity. Or maybe there wasn't enough matter to stop the expansion completely, and the universe would expand forever, but at an ever-decreasing rate. These seemed like the only two options. Expansion, either slowing to a stop or slowing gradually forever. But gravity, the attractive force, should definitely be slowing things down. That was the assumption. In 1998, two independent teams of astronomers set out to measure exactly how much the universe's expansion was decelerating. They used supernovae, massive stellar explosions that can be seen across billions of light years, as cosmic distance markers. Because supernovae have fairly predictable brightness, astronomers can use them to measure how far away things are and how fast they're receding. Both teams expected to measure deceleration. They expected to quantify how much gravity was slowing the universe's expansion. What they discovered instead was so unexpected, so contrary to everything they thought they knew, that they initially assumed they'd made a mistake. The universe's expansion wasn't slowing down, it was speeding up. Distant galaxies were accelerating away from us. The expansion of space itself was getting faster over time. Something was pushing the universe apart, overcoming gravity's pull, and this something was getting stronger as the universe aged. This made no sense. Gravity is attractive. It pulls things together. There was no known force or energy that should cause the universe to expand faster and faster. It was like throwing a ball into the air and watching it accelerate upward instead of slowing down and falling back. It violated everything physicists expected. The discovery earned the lead scientist the 2011 Nobel Prize in Physics, but it also created a profound mystery. What could cause accelerating expansion? The answer, or rather the placeholder for our ignorance, became known as dark energy. Here's what we know about dark energy, which isn't much. It constitutes roughly 68% of the universe's total mass energy content. That makes it the dominant component of reality. Regular matter is 5%, dark matter is 27%, and dark energy is the remaining 68%. Most of the universe is this mysterious energy pushing space apart. Dark energy appears to be uniformly distributed throughout space. It's not concentrated in galaxies or galaxy clusters like dark matter. Instead, it seems to fill every point in space with the same density. As space expands, more space is created, and more dark energy comes with it. The total amount of dark energy in the universe is increasing because there's more volume, and that increasing dark energy causes faster expansion, which creates more volume, which creates more dark energy, in an accelerating cycle. This is different from dark matter, which gets more spread out as the universe expands. Dark energy's density stays constant or possibly increases, making it increasingly dominant over time. In the early universe, dark matter's gravitational influence was stronger than dark energy's repulsive effect, allowing galaxies and structure to form. But as the universe expanded and dark energy's influence grew, it began to dominate, accelerating the expansion and eventually preventing any new large-scale structures from forming. But what is dark energy? That's the mystery. We have some ideas, some theoretical possibilities, but nothing confirmed. The leading hypothesis is that dark energy is a property of space itself. Remember that in quantum physics, what we call empty space isn't really empty. It seethes with quantum activity, virtual particles constantly appearing and disappearing, quantum fields fluctuating at the smallest scales. This quantum vacuum has energy, called vacuum energy or zero-point energy. Physicists have known about vacuum energy for decades. What they didn't expect was that it might have large-scale effects on the entire universe. but if vacuum energy has a property called negative pressure, a kind of anti-gravity effect, it could cause space to expand. And because this energy is a property of space itself, as space expands, there's more space and thus more vacuum energy, causing faster expansion. This sounds promising, but there's a huge problem. When physicists calculate how much vacuum energy should exist based on quantum field theory, they get a number that's enormously different from what we observe. The theoretical value is about 10 to the power of 120 times larger than the observed value. That's not a small discrepancy. It's one of the worst mismatches between theory and observation in all of physics. Something is very wrong with either our quantum theories or our understanding of how vacuum energy relates to dark energy. Another possibility involves something called the cosmological constant. When Einstein was developing general relativity, he initially believed the universe was static, neither expanding nor contracting. But his equations indicated the universe should be unstable, either collapsing or expanding. To make the math work for a static universe, he added a term to his equations called the cosmological constant, a repulsive force that could balance gravity's attraction. Later, after Hubble discovered the expanding universe, Einstein reportedly called the cosmological constant his greatest blunder and removed it from his equations. But ironically, dark energy behaves exactly like a cosmological constant would. It's a constant energy density of space that produces a repulsive gravitational effect. Einstein's blunder might actually be one of his greatest insights. If dark energy is a cosmological constant, that means it's a fundamental property of the universe. Built into the very structure of space-time, it would be constant throughout time and space, never changing, always pushing the universe apart. This is the simplest explanation for dark energy, and it matches the observations quite well. But it doesn't explain why the cosmological constant has the particular value it does, or what physical mechanism produces it. Some physicists have proposed more exotic explanations. Maybe dark energy isn't constant but changes over time, a field called quintessence that permeates space and evolves as the universe ages. Maybe it's related to extra dimensions beyond the 3 spatial dimensions we experience. Maybe it's a sign that general relativity breaks down on cosmological scales and needs modification. The truth is, we don't know. Dark energy is perhaps the deepest mystery in all of physics because it touches on fundamental questions about the nature of space, time, energy, and gravity. It suggests that something crucial is missing from our understanding of how reality works at the larger scales. The implications of dark energy are staggering. If the current accelerating expansion continues, the long-term fate of the universe looks increasingly lonely. Galaxies outside our local group will eventually recede so quickly that their light can no longer reach us. The observable universe will shrink as distant structures disappear beyond the cosmic horizon. Billions of years in the future, observers in the Milky Way will see a universe that appears empty, all other galaxies invisible because space has expanded so much that light from them can never bridge the gap. Eventually, if acceleration continues, even structures like galaxies might be torn apart in what physicists call the Big Rip. Space would expand so rapidly that it would overcome the gravitational binding of galaxies, then solar systems, then planets, then atoms themselves, until everything is shredded by the relentless expansion. That's a dark vision of the far future, though it's worth noting that the Big Rip depends on assumptions about dark energy that might not be correct. If dark energy is truly constant, the universe will expand forever, but less catastrophically. Structures will become isolated but not torn apart. Either way, the age of stars and galaxies and life is just a brief chapter in a much longer cosmic story, one increasingly dominated by dark energy's influence. What makes dark energy so scientifically frustrating is that it's everywhere, but we can't study it directly. We can only observe its effects on the universe's expansion. We can't bring it into a laboratory, can't manipulate it, can't isolate it for examination. It's a cosmic scale phenomenon that manifests only in the motion of galaxies over billions of years. That makes testing theories incredibly difficult. But astronomers are trying. New generations of telescopes and surveys are measuring the universe's expansion history with increasing precision, looking for subtle variations that might reveal whether dark energy is truly constant or changes over time. They're studying how dark energy affects the formation of galaxy clusters and the distribution of matter across cosmic scales. They're searching for any clue about what this dominant component of reality might be. Here's something humbling to consider. For most of human history, we thought the universe was made of the stuff we see around us: earth, water, air, fire. Later, atoms and molecules. Then we discovered dark matter, and realized visible matter is only 5% of the total. Now we know that even dark matter is a minority component. Most of the universe is dark energy, something we've only known about for about 25 years, something we understand barely at all. We live in a universe where 95% of the content is unknown. We can detect its effects. We can measure its influence. But we don't know what most of reality is made of. That's a profound statement about the limits of human knowledge, despite all our scientific progress. As you relax tonight, think about the vast cosmic ocean of dark energy surrounding you, filling the space between atoms, between planets, between galaxies. Think about how it's gently pushing the universe apart, steadily, inexorably, determining the fate of everything that exists. And think about how something so important, so dominant, so omnipresent can remain such a complete mystery. Dark energy reminds us that the universe doesn't owe us comprehensibility. Reality is what it is, whether we understand it or not. But humans keep trying to understand anyway, building better instruments, crafting more sophisticated theories, refusing to accept mystery as a final answer, even while acknowledging how mysterious things remain. Every moment of your life you experience something remarkable. Right now, as you read or listen to these words, you're aware of them. You have a subjective sense of being you, of experiencing thoughts and sensations and emotions. There's something it's like to be you, to see colours, to feel textures, to remember the past, to imagine the future. This inner experience, this sense of awareness, is what philosophers and scientists call consciousness. And despite being the most intimate, immediate aspect of your existence, it might be the deepest mystery in all of science. The mystery of consciousness isn't about how the brain works mechanically. Neuroscientists have made enormous progress mapping the brain structure, understanding how neurons fire and connect, identifying which brain regions are involved in different functions. We know that vision is processed in the occipital lobe, that language involves Broca's and Wernicke's areas, that emotions are influenced by the limbic system, that memory formation involves the hippocampus. We can watch brain activity in real time using functional MRI, seeing which regions light up when someone solves a math problem or looks at a face or recalls a memory. We can trace neural circuits, map synaptic connections, measure neurotransmitter levels. We understand a great deal about the brain's mechanics, but understanding those mechanics doesn't explain the hardest question about consciousness. It doesn't explain why there's subjective experience at all. Why is there something it feels like to see the colour red? Why does pain hurt instead of being just an information signal? Why is there an inner mental life, a private world of experiences that you alone can access? This is what philosopher David Chalmers famously called the hard problem of consciousness. The easy problems, though easy is definitely tongue-in-cheek because they're incredibly difficult, involve explaining the brain's functions, how we process information, how we integrate sensory inputs, how we form memories and make decisions. These are questions about mechanisms and can in principle be answered by studying neurons and their connections. But the hard problem is different. It asks, why do those mechanisms generate subjective experience? Why isn't the brain just an unconscious information processor like a very sophisticated computer? Why is there phenomenal consciousness, the felt quality of experience? Consider your experience of the colour red. When you see something red, light of certain wavelengths enters your eye, strikes photoreceptors in your retina, which send electrical signals through the optic nerve to your brain, where various visual cortex regions process the information about colour, shape, motion, and context. Neuroscientists can trace this entire pathway. They can tell you exactly which neurons fire, which neurotransmitters are released, which brain regions activate. But none of that explains the subjective experience of redness, what philosophers call the quale, plural qualia, of seeing red. The particular way red looks to you, the qualitative feel of the experience, seems to be something over and above the physical processes in your brain. You can't convey what red looks like to someone who's never seen colours. No amount of describing photon wavelengths or neural activation patterns captures the experience itself. This creates what's called the explanatory gap. There seems to be an unbridgeable gulf between objective descriptions of brain activity and subjective experiences of consciousness. You can know everything about neurons and still not understand why consciousness exists. Some philosophers and scientists argue there's actually no mystery here at all. They say consciousness is nothing more than complex information processing. When a brain reaches a certain level of complexity and integration, consciousness naturally emerges, just as wetness emerges from collections of water molecules, or traffic jams emerge from many cars interacting. There's no special source, no mysterious ingredient. Consciousness is just what complex information processing feels like from the inside. This view, called functionalism or identity theory, says that mental states are identical to physical brain states. When you experience pain, that experience just is certain neurons firing in certain patterns. There's nothing additional to explain. The feeling is the physical process, viewed from a first-person perspective rather than a third-person scientific perspective. Other philosophers and neuroscientists aren't satisfied with this answer. They argue that even if we perfectly understood every neuron and synapse, we still wouldn't have explained why there's subjective experience. Even if we could predict and manipulate consciousness with perfect accuracy, the hard problem would remain. Why is there consciousness at all, rather than just unconscious information processing? One famous thought experiment illustrating this is called the philosophical zombie. Imagine a being physically identical to a human in every way. Same atoms, same neurons, same brain structure and activity. But this being has no consciousness. There's nothing it's like to be a philosophical zombie. It's dark inside. The zombie behaves exactly like a conscious human, responding to stimuli, speaking, seeming to experience emotions, but it's all just mechanical response with no inner experience. Some philosophers argue that philosophical zombies are conceivable, and if they're conceivable, they're possible in some sense. And if they're possible, that means consciousness is not reducible to physical processes alone. There must be something additional, something non-physical about consciousness. Other philosophers argue that philosophical zombies are not actually conceivable, that they involve a logical contradiction we don't recognize. If something has a human brain with human neural activity, consciousness necessarily exists. The zombie scenario is impossible, not just practically, but logically. This debate touches on deep questions about the nature of reality itself. Is consciousness purely physical, entirely explicable in terms of neurons and neurotransmitters? Or does consciousness involve something non-physical, something that can't be reduced to material processes? Most scientists strongly favour physicalist explanations. The brain is a physical object made of atoms obeying physical laws. Consciousness must somehow emerge from those physical processes, even if we don't yet understand how. The alternative, that consciousness involves non-physical properties or substances, seems to require abandoning scientific naturalism, the foundation of modern science. But the hard problem persists even for physicalists. Several theories have been proposed to bridge the explanatory gap, to explain how physical processes generate subjective experience. One prominent theory is integrated information theory, developed by neuroscientist Giulio Tononi. This theory proposes that consciousness corresponds to integrated information. A system is conscious to the degree that it integrates information in a unified way. The theory provides a mathematical framework for calculating how much consciousness a system should have based on its information integration. According to integrated information theory, consciousness exists on a spectrum. Simple systems like thermostats have tiny amounts of consciousness because they integrate very little information. Human brains have rich consciousness because they integrate vast amounts of information in complex ways. The theory makes testable predictions about which brain states should be conscious and which shouldn't. Another influential theory is global workspace theory, proposed by Bernard Baars. This theory likens consciousness to a bright spotlight on a dark stage. At any moment, many unconscious processes occur in your brain, like actors in the dark areas of a stage. But only information that enters the global workspace, the spotlight area, becomes conscious. This workspace allows different brain regions to share and integrate information, making it available for planning, decision-making, and verbal report. Global workspace theory explains why we can only be consciously aware of a small amount of information at once, even though our brains process enormous amounts of information unconsciously. It also explains phenomena like inattentional blindness, where people fail to notice obvious things when their attention is focused elsewhere. A third approach involves quantum mechanics. Some scientists, most notably Roger Penrose and Stuart Hameroff, have proposed that consciousness involves quantum processes in the brain's microtubules, tiny structures inside neurons. They argue that quantum effects like superposition and entanglement might play a role in generating consciousness, and that classical physics alone can't explain it. This quantum consciousness theory is highly controversial. Most neuroscientists doubt that quantum effects could persist long enough in the warm, wet environment of the brain to influence cognition. But the theory hasn't been definitively ruled out, and it continues to attract interest because it attempts to explain consciousness using physics rather than just neurobiology. None of these theories has fully solved the hard problem. Each provides insights into aspects of consciousness, but none has explained to everyone's satisfaction why subjective experience exists at all. The explanatory gap remains. Some philosophers and scientists argue that maybe the hard problem is unsolvable, not because we lack sufficient knowledge, but because we're asking the wrong questions, or because human cognition has inherent limitations. Philosopher Colin McGinn has proposed that just as a dog can't understand quantum mechanics, humans might lack the cognitive capacity to understand consciousness. The problem might be permanently mysterious to us. Others argue that the hard problem is a pseudo-problem, arising from conceptual confusions rather than deep mysteries. Philosopher Daniel Dennett, for instance, argues that consciousness is not a single, unified phenomenon, but a collection of cognitive abilities that can each be explained functionally. The feeling that there's something mysterious left over after explaining those functions is an illusion, a trick our brains play on us. The debate continues, vigorous and unresolved. Meanwhile, neuroscience keeps advancing, revealing more about how brains work, how consciousness correlates with neural activity, how it can be altered by drugs or brain damage or meditation. We're learning to predict and influence consciousness with increasing precision. But prediction and influence don't equal understanding. You can predict how an engine works without understanding why the combustion of fuel creates force. Similarly, we might be able to predict and manipulate consciousness perfectly, while still not understanding why it exists at all. Here's another fascinating angle on the consciousness mystery. We don't even know which other creatures are conscious. Are animals conscious? Most people would say yes for mammals, especially for creatures like dolphins and elephants and primates that show signs of intelligence and emotion. But what about fish? Insects? What about individual neurons? Where does consciousness begin and end in the tree of life? Some philosophers argue that consciousness might be more widespread than we imagine, a property not just of brains, but of any system that integrates information. This view, called panpsychism, suggests that consciousness in some form might exist even in simple systems, possibly even in individual particles. Human consciousness would then be the result of integrating these simple conscious elements into complex patterns. This sounds bizarre, but some serious thinkers take panpsychism seriously as a way to avoid the hard problem. If consciousness is a fundamental property of matter, like mass or charge, then there's no mystery about how it emerges from non-conscious components. It was always there, just in simpler forms. As you drift tonight, consider your own consciousness. The fact that you experience anything at all, that there's something it's like to be you, is arguably the most profound fact about your existence. And it's something science can describe, correlate, predict, and manipulate but can't quite explain. Your consciousness right now might be the universe becoming aware of itself, matter organized in such a way that it experiences its own existence. Or it might be something stranger still, something we don't have the conceptual frameworks to understand. Either way, every moment of awareness, even the drowsy moments before sleep, is a reminder that reality contains depths we've barely begun to fathom. The mystery of consciousness isn't just an abstract philosophical puzzle. It's intimately connected to questions about personal identity, free will, the possibility of artificial consciousness, the nature of death, and what it means to be human. Solving the hard problem would transform not just neuroscience, but our entire understanding of our place in the universe. For now, consciousness remains mysterious, familiar yet unexplained, immediate yet elusive. The most certain thing about your existence, the one thing you know beyond doubt that you are experiencing, is also the thing science struggles most to account for. What a beautiful paradox. The universe is unimaginably vast. Our Milky Way galaxy alone contains somewhere between 100 and 400 billion stars. Most of those stars have planets orbiting them. The number of potentially habitable planets in our galaxy is measured in billions, and our galaxy is just one of hundreds of billions of galaxies in the observable universe. Given these numbers, given the sheer abundance of potential homes for life, given that Earth developed life relatively quickly after becoming habitable, it seems almost certain that life must have arisen elsewhere. And if life is common, then intelligent life must have evolved on at least some planets. And some of those civilizations must have developed technology, perhaps millions or billions of years before we did. So where is everybody? That's the question physicist Enrico Fermi famously asked over lunch with colleagues in 1950. Given the age and size of the universe, given how many stars and planets exist, alien civilizations should be common. Even if interstellar travel is difficult, any spacefaring civilization could colonize the entire galaxy given enough time, even travelling at just a tiny fraction of light speed. If aliens exist in any significant numbers, we should see evidence of them everywhere. But we don't. Our sky is silent. Our radio telescopes have detected no unambiguous signals from extraterrestrial intelligence despite decades of searching. No alien spacecraft have visited Earth, at least none that have left verifiable evidence. No megastructures built by advanced civilizations are visible in our surveys of distant stars. The universe appears empty of other intelligence. Why? This contradiction between the apparent high probability of alien life and the complete lack of evidence for it is called the Fermi Paradox. It's one of the most fascinating and troubling mysteries in all of science because any answer to it has profound implications. Let's explore the possible solutions to the Fermi Paradox, because there are many, and each paints a different picture of our place in the cosmos. First possibility. Life is incredibly rare. Maybe the origin of life is far more improbable than we think. Maybe Earth is a cosmic fluke, a 1 in a trillion accident where just the right chemicals came together under just the right conditions to spark the first self-replicating molecules. If life itself is vanishingly unlikely, then we might be alone in the observable universe despite all those billions of planets. This is the rare Earth hypothesis, and it has some support. We don't fully understand how life began on Earth. We know it happened relatively quickly in cosmic terms, within 1 billion years of Earth's formation, but we don't know how. Every hypothesis for life's origin requires a series of seemingly unlikely events, just right conditions that had to persist long enough for chemistry to become biology. Maybe those conditions are incredibly rare. Maybe most planets are too hot or too cold, too close to their stars or too far away, too geologically active or too geologically dead, too bombarded by radiation or too chemically stable. Maybe the window where life can emerge is vanishingly small, and Earth just happened to hit it while countless other worlds did not. Second possibility: life is common, but intelligent life is rare. Maybe microbial life exists on many planets, but it rarely evolves beyond simple forms. On Earth, life remained single-celled for billions of years before multicellular organisms appeared. Complex life required a series of evolutionary breakthroughs, each one individually unlikely. Maybe on most worlds, life never gets past the bacterial stage, and intelligence might be even rarer. On Earth, among millions of species, only one has developed technology. Dolphins are intelligent but never built cities. Octopuses are smart but live underwater where technology is nearly impossible. Crows and parrots are clever but lack the physical structure to manipulate tools effectively. Intelligence might be evolutionarily useful, but technological intelligence might be such a specific combination of factors: brain power, social structure, long lifespan, appropriate anatomy, that it almost never emerges. Third possibility: intelligent technological civilizations exist but are incredibly short-lived. Maybe there's a great filter, a barrier that almost no civilization survive. That filter might be ahead of us, which is a terrifying thought. It would mean that civilizations typically destroy themselves shortly after developing technology, perhaps through nuclear war, environmental collapse, AI gone wrong, or some other catastrophe we haven't even imagined yet. If the great filter is ahead of us, then the silence of the cosmos is ominous. It means we're approaching a test that almost all civilizations fail. The fact that we haven't heard from anyone else means they didn't survive long enough to make contact, and we probably won't either. Alternatively, maybe the great filter is behind us, something in Earth's past that was so improbable that most planets never make it through. Maybe it was the origin of life itself, or the development of eukaryotic cells, or the evolution of multicellular organisms. If the filter is behind us, then we're incredibly lucky survivors, but that would mean intelligent life is extremely rare. Fourth possibility: alien civilizations exist but remain hidden deliberately. This is called the zoo hypothesis, or the planetarium hypothesis. Maybe advanced aliens have some version of a prime directive like in Star Trek, where they don't interfere with less developed civilizations. They observe us from afar, letting us develop naturally, perhaps until we reach some threshold of technological or ethical development. Or perhaps aliens hide because the universe is dangerous. The dark forest hypothesis, popularized by science fiction author Liu Cixin, suggests that any civilization that reveals itself gets destroyed by other hostile civilizations. In this scenario, the galaxy is full of life, but everyone is hiding, silent and afraid, knowing that making noise invites annihilation. This explains the Fermi Paradox, but requires that every single civilization adopts the same strategy of silence, which seems improbable unless there's a very good reason for it, like a genuinely dangerous predator species that punishes any civilization that reveals itself. Fifth possibility: we're living at the wrong time. Maybe civilizations are common, but the universe is so old and space is so vast that civilizations rarely overlap in time and space. When a civilization broadcasts for 1 million years, that sounds like a long time to us. But it's a cosmic instant. If civilizations emerge randomly over billions of years across billions of star systems, the chance that two civilizations exist simultaneously close enough to detect each other might be vanishingly small. We might be early. We might be among the first technological civilizations to emerge in our region of the galaxy. In another billion years, the sky might be full of alien signals and megastructures, but right now, at this particular moment in cosmic history, we're essentially alone. Sixth possibility. They're here, but we don't recognize them. Maybe alien intelligence is so different from ours that we can't detect or understand it. We look for radio signals and physical artifacts, but what if aliens communicate through gravitational waves, or quantum entanglement, or some technology we haven't imagined? What if they've transcended physical form entirely, existing as patterns of information in some medium we don't recognize? Or what if they're right here on Earth, in forms we don't recognize as intelligent? What if there's intelligence in ecosystems, in the global biosphere, in processes we consider non-living? Our definition of intelligence and consciousness is human-centric. Truly alien intelligence might be so alien we're looking right at it without seeing it. Seventh possibility, they exist but have no interest in us. Maybe advanced civilizations don't explore or colonize because there's no point. Maybe they've transitioned to virtual reality, preferring simulated worlds to physical space exploration. Maybe they've achieved something like enlightenment or post-scarcity existence, where curiosity about other species has been superseded by internal pursuits. Or maybe the universe is colonized, but Earth happens to be in a backwater, a rural province of no interest to anyone. We assume aliens would want to contact or visit us, but why should they? We might be as interesting to them as ants are to us, worth studying briefly perhaps, but not worth sustained contact. Eighth possibility. We're in a simulation. This sounds like science fiction, but some serious philosophers and physicists take it seriously. If it's possible to create realistic simulations of universes, and if advanced civilizations create many such simulations, then statistically, we're more likely to be living in a simulation than in base reality. If we're in a simulation, the Fermi Paradox might be explained by the simulation's design. Perhaps the programmers didn't bother simulating other civilizations, or they're keeping us isolated as a controlled experiment. Ninth possibility, interstellar travel is harder than we think. Maybe there's no practical way to cross the enormous distances between stars. Light takes years to reach even the nearest stars. Anything moving slower takes decades, centuries, or millennia. Maybe civilizations never physically colonize other star systems because it's simply too difficult, too expensive, too time-consuming. They might communicate through radio waves but never actually travel. This would explain why we don't see evidence of alien colonies or megastructures, though it wouldn't explain why we don't hear alien radio transmissions unless civilizations typically don't broadcast or don't broadcast for very long. 10th possibility, we haven't looked long enough or carefully enough. SETI, the search for extraterrestrial intelligence, has been operating for about 60 years. That sounds like a long time, but the galaxy is enormous. We've examined perhaps a few thousand stars carefully out of hundreds of billions. We've listened to a tiny fraction of the possible radio frequencies for a cosmic eye blink of time. Maybe aliens are broadcasting, but we haven't looked in the right direction yet, or at the right frequency, or for long enough to catch a signal. Maybe we need to search for centuries before we have any real chance of success. The absence of evidence isn't evidence of absence, especially when you've barely begun to search. Each of these solutions to the Fermi Paradox is fascinating in its own way, and each has different implications for humanity's future. If life is rare, we bear an enormous responsibility to preserve and protect it, because we might be the only example in a vast, sterile cosmos. If the great filter is ahead of us, we need to be very careful about how we develop technology and manage existential risks. If aliens are deliberately hiding, maybe we should be cautious about broadcasting our presence. The Fermi Paradox forces us to confront deep questions. Are we alone? Are we special? Are we in danger? What does our apparent solitude tell us about the nature of life, intelligence, and technological development? Some people find the Great Silence comforting. It means no alien invasion, no hostile advanced civilizations waiting to conquer or exploit us. We can develop at our own pace without external interference or competition. Others find it lonely, even tragic. To be alone in the universe, to have no one to talk to, no cosmic peers, no one who has faced the same challenges and might offer wisdom or companionship, feels like a profound loss. The universe is so vast, so full of wonders, and yet we might be the only ones capable of appreciating it, and some find it motivating. If we are alone or nearly alone, then we have a cosmic mission. We might be the universe's best or only shot at producing intelligence, science, art, and meaning. What we do, whether we survive and flourish or destroy ourselves, might matter on a cosmic scale if no one else is out there doing it. Personally, I find the Fermi Paradox one of the most simultaneously exciting and humbling mysteries in science. Every solution teaches us something, whether about the universe's nature or about humanity's place within it. The silence might be temporary, a problem to be solved by better instruments and longer searches, or it might be profound, a fundamental truth about reality that we'll need to accept and live with. As you rest tonight, think about that great silence. Imagine the hundreds of billions of stars in our galaxy alone, each potentially hosting planets, many of those planets potentially habitable, and yet, as far as we can tell, they're all silent. No one calling out, no one answering, just us on our little world, looking up and wondering. Maybe tomorrow we'll detect a signal, a clear, unambiguous message from someone else saying, "We're here too." That would be one of the greatest moments in human history. Or maybe we'll search for centuries and hear nothing, gradually accepting that we might truly be alone, or so isolated that contact is impossible. Either way, the mystery remains. The Fermi Paradox sits there, challenging our assumptions, inviting us to think deeply about what it means to be alive and intelligent in a universe that might or might not contain others like us. Where is everybody? It's a simple question, with profound implications, and we don't yet know the answer. Now we're going to venture into the strangest territory in all of science, a realm where particles can be in two places at once, where observing something changes what it is, where cause and effect blur together, and where the very notion of objective reality becomes questionable. Welcome to the quantum world. Quantum mechanics is arguably the most successful scientific theory ever developed. Its predictions have been confirmed to extraordinary precision in countless experiments. It underlies all of modern electronics, from the smartphone in your pocket to the computer running this video. It explains the behavior of atoms, molecules, light, and fundamental particles. It works magnificently. And yet, nobody fully understands what it means. The quantum world operates according to rules that violate our everyday intuitions about how reality should work. And these aren't just theoretical oddities. These are real, experimentally verified phenomena that force us to question basic assumptions about the nature of existence itself. Let's start with one of the most famous quantum mysteries, wave-particle duality. Light can behave as both a wave and a particle, depending on how you measure it. Shine light through a narrow slit, and it diffracts like a wave, creating interference patterns. But detect individual photons, and light acts like discrete particles, tiny bullets of energy. This isn't just light. Electrons, atoms, even large molecules all exhibit this wave-particle duality. They're not waves or particles. They're something else, something that can manifest as either depending on the experimental setup. Quantum mechanics calls this something a wave function, a mathematical description that contains probabilities for all possible outcomes. The wave function itself isn't physical in the way we normally understand. It's more like a catalogue of potentialities, of things that might happen. And here's where it gets truly strange. According to quantum mechanics, before you measure a quantum system, it exists in a superposition, simultaneously in all possible states. An electron can be in multiple places at once, spinning both up and down simultaneously, existing in a ghostly combination of all possibilities. Only when you observe or measure the system does it collapse into a definite state. Before measurement, the electron has no definite position. It's spread out, existing probabilistically everywhere its wave function describes. The act of measurement somehow forces it to choose, to become localized in one spot. This is the famous measurement problem of quantum mechanics, and it's deeply mysterious. What counts as a measurement? Does it require a conscious observer, or will any interaction with the environment do? What physically happens during wave function collapse? How does a system go from being in many states simultaneously to being in just one? Different interpretations of quantum mechanics offer different answers, and none of them are satisfying. The Copenhagen interpretation says the wave function collapse is fundamental, but offers no mechanism for how or why it occurs. It essentially declares measurement special without explaining what makes it special. The many worlds interpretation suggests that wave function collapse doesn't actually happen. Instead, every possible outcome of a measurement occurs in a different branch of reality. When you measure that electron's position and find it here, there's another version of you in another universe who measured and found it there. All possibilities are realized, just in separate, non-communicating parallel universes. This solves the measurement problem at the cost of requiring an infinity of parallel universes, constantly branching every time any quantum event has multiple possible outcomes, which is constantly at every scale from fundamental particles to galaxies. Most physicists find the ontological extravagance of many worlds troubling, though it's mathematically elegant. Other interpretations, like pilot wave theory or objective collapse models, offer different solutions, each with their own strengths and problems. After a century of quantum mechanics, we still don't have consensus on what the theory is telling us about reality. Then there's quantum entanglement, which Einstein famously called spooky action at a distance. When two particles become entangled, which can happen when they're created together or interact, they remain correlated even when separated by vast distances. Measure one particle, and you instantly affect the state of the other, no matter how far apart they are. This isn't a matter of the particles carrying hidden information, as Bell's theorem famously proved. The correlation between entangled particles is stronger than any classical correlation could be. It's as if measuring one particle instantly sends information to the other, updating its state faster than light could travel between them. Quantum entanglement doesn't allow faster than light communication. We can't use it to send messages, but it does show that reality is fundamentally non-local. What happens here can instantly influence what happens there, not through any physical connection, but through the mysterious quantum correlation Einstein found so troubling. Entanglement is now being harnessed for practical applications like quantum computing and quantum cryptography, but using it doesn't resolve the mystery of how it works. We can predict and control entanglement precisely, but we don't really understand what it means about the nature of space, time, and causality. Another quantum mystery involves the principle of complementarity. Niels Bohr proposed that some properties of quantum systems are complementary, meaning you can measure one or the other but never both precisely at the same time. Position and momentum are complementary. So are energy and time. The more precisely you know one, the less precisely you can know the other. This isn't due to limitations in our measuring instruments. It's a fundamental feature of reality. The properties don't have definite simultaneous values. Heisenberg's uncertainty principle formalizes this. There's a fundamental limit to how precisely you can know complementary properties. This uncertainty isn't ignorance. It's not that the properties have values we just can't measure. The properties genuinely don't have definite values simultaneously. Reality itself is fuzzy at quantum scales. This has philosophical implications that philosophers and physicists still wrestle with. If properties don't have definite values until measured, does that mean the observer creates reality? Or does it mean reality is more probabilistic and less determinate than we imagined? What does it mean for something to be real if its properties depend on whether and how we measure them? Quantum tunneling is another phenomenon that defies classical intuition. A particle encountering an energy barrier it shouldn't be able to cross can sometimes appear on the other side anyway, as if it tunneled through. This isn't just a curiosity. Radioactive decay depends on quantum tunneling. So does nuclear fusion in the sun. Life itself relies on quantum processes. From a classical perspective, tunneling seems impossible. The particle doesn't have enough energy to overcome the barrier, but quantum mechanically, the particle's wave function extends beyond the barrier, giving it a non-zero probability of being found on the other side. And sometimes it is. There's no gradual process of tunneling through. The particle doesn't bore a hole or climb over. It's on one side, and then, without passing through the intermediate space, it's on the other. Cause and effect seem to disconnect in these quantum transitions. Quantum decoherence, the process by which quantum systems lose their quantum properties and start behaving classically, is another active area of research and mystery. When quantum systems interact with their environment, their superpositions collapse, and they behave more like ordinary objects. This explains why we don't see macroscopic quantum effects in everyday life. Large objects constantly interact with countless environmental particles, causing rapid decoherence. But where exactly is the line between quantum and classical behaviour? Is there a fundamental size or complexity above which quantum effects disappear? Or is decoherence gradual and context-dependent? Could there be macroscopic quantum effects under the right conditions? We don't fully know. And then there's quantum field theory, which describes particles not as point-like objects, but as excitations in underlying quantum fields permeating all of space. What we think of as empty space is actually a seething quantum foam, where virtual particles constantly appear and disappear, where fields fluctuate, where the vacuum itself has structure and energy. This quantum vacuum is the source of some of physics' deepest mysteries, including the cosmological constant problem related to dark energy. The energy of the quantum vacuum, calculated from quantum field theory, is enormously different from the observed dark energy density. Either our calculation is wildly wrong, or there's a cancellation mechanism we don't understand. All of these quantum mysteries share a common theme. They reveal that reality at its most fundamental level is profoundly different from the reality we experience in everyday life. Particles aren't tiny billiard balls. They're probability clouds that crystallize into definiteness only when observed. Causality isn't always clear. Objects can be in multiple states simultaneously. Properties don't have definite values independent of measurement. Quantum mechanics forces us to confront deep questions about the nature of reality, the role of observation, the meaning of physical properties, and the limits of human comprehension. It works spectacularly well as a predictive tool, but its ontological implications remain hotly debated. Some physicists embrace the mystery, arguing that quantum mechanics is telling us something profound about reality's fundamental nature that we're still learning to understand. Others argue that the mystery arises from asking the wrong questions, or clinging to classical intuitions that quantum mechanics has shown to be false. As you drift towards sleep, perhaps you can appreciate the strangeness of the quantum world. The atoms in your body, the neurons in your brain, everything about you is ultimately quantum. You exist at the nexus of trillions upon trillions of quantum events, wave functions collapsing, particles entangling, tunneling, interfering. The solidity you feel, the definiteness of your existence, emerges from an underlying reality that's ghostly, probabilistic, and deeply mysterious. Quantum mechanics works. It predicts. It enables technology. But what it means, what it tells us about the true nature of reality, remains one of science's deepest and most beautiful mysteries. How did life begin? It's one of the most fundamental questions we can ask, and despite decades of research, we still don't have a complete answer. We know life exists, that's obvious. We know it's been around for at least 3.8 billion years on Earth. We know it's based on chemistry, on the interactions of molecules following physical laws. But the transition from non-living chemistry to living biology, That moment when inanimate matter became animate remains deeply mysterious. Life, as we understand it, requires several key features. It needs metabolism, a way to acquire and use energy. It needs reproduction, a way to make copies of itself. It needs heredity, a way to pass information from one generation to the next. And it needs evolution, a way for that hereditary information to change over time, allowing adaptation. Modern life accomplishes all of this through an intricate system involving DNA, RNA, and proteins. DNA stores genetic information. RNA helps translate that information, and in some cases stores it too. Proteins do most of the actual work, catalyzing chemical reactions, building structures, transporting molecules. It's an elegant system, refined by billions of years of evolution. But here's the problem. This system is complex, interdependent. DNA needs proteins to replicate. Proteins need DNA to code for them. RNA bridges the two but is itself complex. How could such an intricate system arise from scratch? It seems like a chicken and egg problem. Which came first, the information storage system or the machinery to read and use that information? Scientists have proposed numerous hypotheses for how life originated, and this is an active, vibrant area of research. Let's explore some of the leading ideas. The primordial soup hypothesis, one of the oldest ideas, suggests that early Earth's oceans contained a rich mixture of organic molecules, amino acids, sugars, nucleotide bases, formed by chemical reactions in the atmosphere and delivered by meteorites. Lightning, ultraviolet light, and volcanic activity provided energy. In this chemical soup, molecules randomly combined, eventually forming more complex structures that could replicate. The famous Miller-Urey experiment in 1953 showed this was possible in principle. They simulated early Earth conditions, passing electrical sparks through a mixture of water, methane, ammonia, and hydrogen. After a week, they found amino acids, the building blocks of proteins. Later experiments produced even more complex organic molecules. So we know organic molecules, the ingredients of life, can form naturally from simple chemicals and energy. That's encouraging. But it's a long way from amino acids to a living cell. The gap between chemistry and biology is vast. One hypothesis for bridging that gap is the RNA world. This suggests that before DNA and proteins, there was a simpler system based entirely on RNA. RNA can both store information like DNA and catalyze reactions like proteins. Some RNA molecules, called ribozymes, are natural catalysts. Perhaps early life was entirely RNA-based, with RNA molecules that could replicate themselves and catalyze the chemical reactions they needed. This solves the chicken and egg problem. You don't need DNA and proteins if RNA can do both jobs. Over time, as the system evolved, DNA took over information storage because it's more stable, and proteins took over catalysis because they're more versatile. But initially, RNA might have been sufficient to get life started. The RNA world hypothesis is elegant, but it has challenges. RNA is complex and relatively fragile. How would RNA molecules form spontaneously? How would they replicate accurately without sophisticated machinery? How would early RNA-based life avoid being destroyed by UV radiation or chemical degradation? Another idea focuses on metabolism rather than replication. The metabolism first hypothesis suggests that before life could reproduce, it needed an energy source, a way to maintain itself against entropy. Perhaps the first proto-life was a self-sustaining network of chemical reactions, a metabolic system that could extract energy from the environment and use it to maintain its structure. In this scenario, replication came later, added to already functioning metabolic systems. Life didn't start with information and replication, but with energy and self-maintenance. Heredity was a later innovation that allowed these metabolic systems to persist and evolve. An intriguing variant of metabolism first ideas involves hydrothermal vents, underwater volcanic springs on the ocean floor. These vents create sharp chemical and temperature gradients, with hot, mineral-rich water emerging into cold ocean water. The boundaries between these fluids can form natural compartments and provide energy for chemical reactions. Some researchers propose that life might have originated at these vents, where constant energy flow and natural compartments could have facilitated the chemical reactions needed to get life started. The mineral surfaces around vents might have catalyzed reactions, effectively acting as primitive metabolic systems. Modern bacteria called extremophils thrive in similar hot, chemically harsh environments, suggesting that life might be comfortable in conditions we'd consider extreme. Maybe early life was born in such extremity before adapting to more temperate conditions. Another fascinating approach involves protocells, simple membrane-bound structures that could form spontaneously from lipid molecules. Lipids naturally form membranes in water, creating little bubbles that separate inside from outside. These protocells aren't alive, but they have some lifelike properties. They have boundaries, they can grow and divide, they can concentrate molecules inside them. Perhaps life started with such protocells. Once you have compartments, you can concentrate chemicals, allowing reactions that wouldn't occur in the open ocean. If protocells happen to contain self-replicating molecules, they could reproduce in a primitive sense when they grew large enough to split. Natural selection could then favour protocells with better replication chemistry, gradually refining the system toward modern cells. Clay surfaces have also been proposed as possible sites for life's origin. Clay particles have complex, regular structures that could organise and catalyse chemical reactions. Some researchers suggest that replicating mineral patterns in clay might have preceded biological replication, providing a template that organic molecules later hijacked. Then there's panspermia, the idea that life didn't originate on Earth at all, but was seeded here from elsewhere in space. Meteorites and comets regularly delivered organic molecules to early Earth. Some even contained amino acids and other complex organics. Perhaps they also delivered the first living organisms, or at least the chemical precursors so close to life that the final step to biology was trivial. Panspermia doesn't solve the origin of life problem, it just moves the mystery elsewhere. But it does expand the possible environments and timescales. If life originated somewhere else in the galaxy and then spread to many worlds, including Earth, that might increase the probability that it happened at all. Each of these hypotheses has strengths and weaknesses. None has been proven correct, and it's possible that the true origin of life involved elements from several different ideas. Maybe RNA molecules formed on clay surfaces at hydrothermal vents and became trapped in protocells, where they developed metabolic pathways. The origin of life might have been a complex multi-stage process rather than a single event. What makes the origin of life so mysterious is that we're trying to understand something that happened once, billions of years ago, leaving very little direct evidence. We can't rewind time and watch it happen. We can't even be sure what Earth's conditions were really like when life originated. We have clues from geology and chemistry, but significant uncertainties remain. We also don't know how difficult or easy the origin of life is. Did it happen quickly on Earth, because it's actually quite probable given the right conditions? Or was Earth extraordinarily lucky, a 1 in a trillion fluke? If we ever find life on Mars or on Europa or on Titan or on exoplanets around other stars, that would tell us something important. If life originated independently multiple times, that suggests it's not that difficult. But if we search the galaxy and find life only on Earth, that would suggest it's incredibly rare and unlikely. There's also the question of whether all possible life must be like Earth life. Is DNA, RNA, protein-based life the only way to do it? Or might alien life use completely different chemistry? Silicon-based life has been proposed, though carbon seems far more versatile. Life in liquid methane instead of water has been suggested for Titan. Life in the atmospheres of gas giants, never touching solid surfaces, has been imagined. We don't know the limits of life because we only have one example. Everything we think we know about biology comes from studying Earth life, which all shares a common ancestor. We're studying one outcome of one origin event. Until we find examples of independent origins, we can't know what's universal about life and what's contingent on Earth's particular circumstances. The origin of life connects to several of the mysteries we've already discussed. If life is incredibly rare and difficult to start, that might partially explain the Fermi Paradox. If consciousness emerges naturally from complex information processing, then understanding life's origin helps us understand consciousness's origin. If quantum effects play a role in life's chemistry, as some researchers suspect, then quantum mysteries touch biology. As you rest tonight, consider the remarkable fact of your existence. You're made of atoms forged in dying stars billions of years ago. Those atoms became part of Earth, then through processes we're still trying to understand, they became part of the first living things. Through an unbroken chain of reproduction stretching billions of years, the descendants of those first organisms eventually became you. Every cell in your body carries that ancient heritage. Your DNA contains echoes of innovations made by organisms billions of years ago. The chemical reactions powering your metabolism are refined versions of reactions that first emerged in the earliest life. You're a continuation of something that started long ago in circumstances we're still piecing together. The mystery of life's origin is also the mystery of your origin, your ultimate origin. Where you came from, where all life came from, is a question science is actively working to answer. And one day, we might know. We might recreate that moment when chemistry became biology, when the first molecules began to replicate and metabolize and evolve. When that happens, it will be one of humanity's greatest achievements, understanding how we went from stardust to sentience. All things end. Stars exhaust their fuel and die. Planets cool and cease to be geologically active. Even black holes evaporate eventually through a process called Hawking radiation, though it takes unimaginably long. What about the universe itself? Will it too end? And if so, how? The fate of the universe is intimately connected to its expansion, which we talked about earlier in the context of dark energy. We know the universe is expanding. We know that expansion is accelerating. But what does that mean for the long-term future? Cosmologists have considered several possible fates for the universe, and which one is correct depends on factors we're still trying to measure precisely. The amount of matter and energy in the universe, the nature of dark energy, and whether the laws of physics remain constant over cosmic timescales. One possibility is the Big Crunch. If the universe contained enough matter, gravity would eventually overcome the expansion, causing the universe to contract. Galaxies would start approaching each other instead of receding. The cosmic microwave background would get hotter. Eventually everything would collapse back into a singularity, perhaps similar to the Big Bang, but in reverse. The Big Crunch was once considered likely, but observations of accelerating expansion have made it seem improbable. Unless dark energy somehow reverses, which we have no reason to expect, gravity won't win. The universe will keep expanding. Another possibility is the Big Freeze or heat death. If expansion continues but dark energy remains constant, the universe will expand forever at an accelerating rate. Galaxies beyond our local group will recede until they cross the cosmic horizon and disappear from view. Star formation will eventually cease as gas is used up and not replenished. Existing stars will burn out and die. In this scenario, trillions of years from now, galaxies will be dark, cold graveyards of dead stars, black holes, and stellar remnants. Even black holes will eventually evaporate through Hawking radiation, taking many Google years, a Google being 10 to the power of 100, incomprehensibly long. After black hole evaporation, the universe would consist of diffuse radiation and occasional subatomic particles, spread so thin that interactions are rare. The temperature would approach absolute zero. Entropy would approach its maximum. Nothing interesting would ever happen again. This is called heat death. The universe running down like a clock that's wound up once and slowly ticks towards stillness. It's a bleak picture, but there's a strange beauty to it too. The universe would persist forever, empty but eternal, a vast dark stage where nothing plays out, energy dissipated and dispersed beyond recovery. A third possibility is the Big Rip. If dark energy isn't constant but grows stronger over time, the universe's expansion could accelerate so dramatically that it eventually tears everything apart. First, galaxy clusters would be pulled apart, then galaxies, then solar systems, then planets, then atoms, then perhaps even space-time itself. This would happen in finite time, perhaps tens of billions of years from now. The universe would end not with gradual heat death, but with a sudden violent disintegration. Current observations suggest the Big Rip is unlikely. Dark energy appears to be constant or nearly constant, but we can't rule it out entirely. We don't understand dark energy well enough to be certain it won't change. A fourth scenario involves cyclic universes. Maybe the Big Bang wasn't the beginning, but just the latest in a series of expansions and contractions. Perhaps the universe bounces, expanding after each Big Bang, contracting in a big crunch, then rebounding in another Big Bang. In this view, our universe is just one cycle in an eternal series. Cyclic models are speculative and face theoretical challenges, but they're not impossible. They would mean the universe has no beginning or end, just eternal cycles of expansion and contraction, each cycle perhaps billions or trillions of years long. Another exotic possibility involves vacuum decay. Some theories suggest that what we think of as empty space might not be in its lowest energy state. We might be in a false vacuum, stable, but not as stable as it could be. If that's true, there's some probability that somewhere in the universe space could transition to a lower energy state, creating a true vacuum bubble that expands at light speed, rewriting the laws of physics wherever it touches. Everything inside the bubble would be destroyed, not just killed, but reduced to nothing because the fundamental properties of matter and energy might change. We wouldn't see it coming. It would travel at light speed, so we'd have no warning. One moment, the universe as we know it. The next, transformed into something utterly alien, or nothing at all. This sounds like science fiction, but some physicists take it seriously as a possible fate for the universe. If our vacuum is false, decay is inevitable eventually, though the timescale might be longer than the current age of the universe by many orders of magnitude. Then there's the multiverse possibility. Some theories suggest our universe is just one bubble in a vast cosmic foam, one of infinitely many universes, each with potentially different physical laws, different fundamental constants, different dimensionalities. In some of these other universes, life might be impossible. In others, it might be ubiquitous. We might inhabit the one universe tuned just right for life to exist. If the multiverse is real, our universe's fate is just one story among countless others. Some might end in big crunches, others in big rips, others in heat deaths. And new universes might be constantly forming, making the multiverse eternal, even if individual universes are not. There's currently no way to test multiverse theories, no way to detect other universes if they exist. That makes many physicists uncomfortable. Science deals with what can be observed and tested. If something is in principle unobservable, is it even science? But multiverse theories arise naturally from certain approaches to cosmology and quantum mechanics. They're not invented arbitrarily. They emerge from taking our best theories seriously and following where they lead. What strikes me most about considering the universe's fate is the timescales involved. We're talking about events trillions or even Googles of years in the future. Human civilization is perhaps 10,000 years old. Life on Earth has existed for a few billion years. The universe itself is about 14 billion years old. These are comprehensible numbers, if barely. But the timescales of cosmic endgames are so vast that they dwarf everything that's come before. The era of stars, the era when the universe is filled with light and energy, and the possibility of life, is a tiny fraction of cosmic history. We live in special times, cosmically speaking, when the universe is young and active. Future civilizations, if any exist trillions of years from now, would inhabit a dark universe where stars are rare or absent, where the cosmic microwave background has cooled to almost nothing, where even black holes are dying. They would look back on our era, the stelliferous era, as a golden age of cosmic abundance. Of course, no life as we know it will survive anything close to those timescales. Earth will be destroyed when the Sun becomes a red giant in about 5 billion years. The Milky Way will collide with Andromeda a few billion years after that, scrambling the structure of both galaxies. Any life descended from Earth life would have to migrate to other stars, other galaxies, continually finding new homes as old ones became uninhabitable. Whether intelligence can persist for trillion-year timescales is an open question. Can consciousness exist without stars and planets? Could advanced civilizations find ways to extract energy from black holes or manipulate dark energy? Could they survive the universe's end by somehow existing outside space-time? These are speculations beyond speculation, but they're worth thinking about because they force us to consider consciousness and life in cosmic contexts. We often think about life in human terms, decades or centuries. But what if the universe could host intelligence for incomprehensibly long periods? What would such intelligence become? What would it think about? Would it remember its origins? Or perhaps intelligence is necessarily ephemeral, a brief spark in a long cosmic night. Maybe consciousness requires stars and chemistry and evolution, and when those era ends, so does the possibility of thought. We don't know. We're asking questions about timescales and possibilities so far beyond our experience that our intuitions fail. But that's what makes cosmology so fascinating. It forces us to think bigger, longer, deeper than we're naturally inclined to do. As you settle into sleep tonight, let your mind expand to contemplate these cosmic timescales. Trillions of years, googles of years, eternities. The universe might persist forever, cold and dark but eternal. Or it might end suddenly or gradually in ways we can barely imagine. Either way, we exist in a special time when stars shine, when planets form, when life is possible. You are here, now, briefly, in the cosmic dawn. You're made of stardust, animated by the energy of long-dead stars, conscious for a few brief decades in a universe that might exist for googles of years. It's humbling and exhilarating in equal measure. The ultimate fate of the universe remains unknown, but we can ask the question. We can gather data, build theories, peer into the deep future with mathematics and observation. That ability to contemplate our own cosmic context might be the universe's most remarkable achievement, matter and energy arranged in such a way that it can think about its own destiny. We've journeyed through some of the strangest, most profound mysteries that science has encountered. From the wow signal to dark matter, from consciousness to the Fermi Paradox, from quantum mechanics to the origin of life, from dark energy to the universe's fate. These aren't idle puzzles or philosophical games. They're genuine mysteries, supported by evidence, studied by thousands of scientists and yet remaining stubbornly unsolved. What do all these mysteries have in common? I think they share a few key features that make them especially fascinating. First, they all emerge from good science. We didn't encounter these mysteries through mysticism or revelation. We found them by looking carefully at the universe, measuring, calculating, and testing our theories. The mysteries exist because our observations don't fit neatly into our understanding. Reality is surprising us. Second, they all touch on fundamental questions about the nature of existence. What is the universe made of? Are we alone? What is consciousness? How did life begin? How will everything end? These aren't technical details. They're the big questions that humans have wondered about since we first became capable of wonder. Third, they all remind us how much we don't know. Despite all our progress, despite all our technology and mathematics and scientific sophistication, we remain profoundly ignorant about basic aspects of reality. We don't know what most of the universe is made of. We don't know if we're alone. We don't know how consciousness works. We don't know how life started. That ignorance isn't a failure, it's an invitation. Every mystery is a frontier, a place where human knowledge ends and the unknown begins. And frontiers are exciting. They're where discoveries happen, where our understanding grows, where the next generation of scientists will make their mark. Fourth, these mysteries connect to each other in interesting ways. The search for dark matter involves quantum physics. The Fermi Paradox touches on the origin of life and the fate of civilizations. Consciousness involves quantum effects in biology according to some theories. Dark energy determines the universe's fate. These mysteries aren't isolated. They're part of an interconnected web of questions about reality's nature. And fifth, these mysteries might have answers that completely transform how we think about existence. Discovering what dark matter is would revolutionize physics. Detecting an alien signal would fundamentally change humanity's self-conception. Solving the hard problem of consciousness would alter our understanding of mind and matter. Understanding life's origin would illuminate biology's deepest foundations. These mysteries matter. They're not just academic curiosities. They're questions about the reality we inhabit. Questions whose answers could reshape civilization. But here's what I find most beautiful about scientific mysteries. We can live with them. We can acknowledge that we don't know, that we might not know for a long time, and yet continue investigating, thinking, wondering. Science doesn't require certainty. It doesn't demand immediate answers. It thrives on questions, on uncertainty carefully explored, on mysteries that inspire rather than frustrate. You don't need to solve these mysteries to appreciate them. You don't need a PhD in physics to feel the wonder of dark matter or quantum entanglement. You don't need to be a neuroscientist to marvel at consciousness. These mysteries belong to everyone. They're part of our shared human heritage, questions we face together, and living in a universe full of mysteries is, in its own way, wonderful. Imagine if we knew everything, if every question had been answered, if reality held no more surprises. That would be boring. It would mean our scientific journey was over, nothing left to discover, nowhere left to explore. But we don't live in that universe. We live in one where dark matter exists, but we don't know what it is. Where signals from space might be aliens or might be natural phenomena. Where consciousness emerges from neurons, but we don't understand how. Where life began somehow, but we can't yet reconstruct how. Where quantum mechanics works perfectly but makes no intuitive sense. We live in a universe that surprises us, challenges us, invites us to keep looking deeper, and that's beautiful. So as you drift off to sleep tonight, take comfort in the mysteries. Let them wash over you, these questions about reality's nature. You don't need to solve them. You don't need to understand every detail. Just appreciate that they exist, that the universe is strange and wonderful and full of surprises. Appreciate that we've made progress. We've gone from knowing almost nothing about the cosmos to knowing enough to identify what we don't know. That's an achievement. We've mapped the territory of our ignorance, outlined the frontiers where knowledge ends, and appreciate that the quest continues. Right now, scientists around the world are working on these mysteries. Telescopes are searching for alien signals and studying distant galaxies. Particle detectors are hunting for dark matter. Neuroscientists are mapping the brain and studying consciousness. Astrobiologists are investigating life's origins. Cosmologists are measuring the universe's expansion and probing its fate. The mysteries are being investigated, questioned, studied. Maybe tomorrow someone will make a breakthrough. Maybe in your lifetime one of these profound questions will finally be answered. That would be extraordinary to witness. Or maybe these mysteries will persist for generations. Maybe your grandchildren will still wonder about dark matter and the Fermi Paradox. Maybe these questions are harder than we imagine, requiring insights and instruments we haven't conceived yet. Either way, the journey continues. Science keeps probing, keep questioning, keep pushing at the boundaries of the known. And we all get to participate, even if just by thinking about these questions, by feeling the wonder they inspire, by supporting the researchers working on them. You've made it through tonight's journey into the unknown. Thank you for joining me on this exploration of science's strangest mysteries. If you enjoyed this deep dive into the enigmas that challenge our understanding of reality, please consider liking this video and subscribing to the channel. It helps us continue creating these thoughtful explorations of science and wonder. Leave a comment if you'd like, sharing which mystery fascinated you most or suggesting topics for future videos. Your engagement helps guide what we create next. Until next time, sleep well, dream deeply,